In 2023, American ice hockey player Adam Johnson was cut by another player's skate blade during an on-ice collision and tragically passed away. What took his life was a steel blade only a few millimeters thick. But on the ice rink, these same narrow ice skates can support the full weight of figure skaters weighing over 50 kilograms, allowing them to glide gracefully on the ice. After 3 revolutions in the air, they can still land safely. How can such a thin blade become the only fulcrum for takeoffs and landings? The answer began 4,000 years ago. On the frozen lakes of northern Europe in the winter morning fog, locals who wanted to move faster for hunting smoothed the ribs of elk and cattle and tied them to their feet with leather straps. They skated directly on the ice. Fast forward to the late Middle Ages. In the Netherlands, with its canals, craftsmen first embedded iron edges into the skates. Skating transitioned from the age of bone skates to the age of metal skates. Modern skating mainly includes figure skating, speed skating, and ice hockey. Figure skating is where the magic of skating is most visible. Figure skating star Yuzuru Hanyu doesn't just stand motionless on a single point of his foot, but rotates around a small arc near the middle in front of the blade, and moves slightly to find the most stable balance position. However, the magic of the ice skate is about far more than spinning. When a skater prepares for a jump that uses the toe pick, the movement looks light, but the takeoff is extremely explosive. The tiny toe pick at the front of the skate bites into the ice, concentrating force onto a point no larger than a fingernail, and creating a temporary anchor on the ice. The skater pushes off and is propelled into the air. It is these small toe picks that make figure skating possible on the ice. If it were speed skating, where the ice skates lack toe picks, and the skater took off in the same way, the skater would only glide smoothly on the ice. It would be hard to generate the force to lift off like in figure skating. Speed skating focuses on long distance, stable, and high-speed gliding, while figure skating requires firmly grasping the ice for a split second to complete these delicate and dexterous jumping movements. After takeoff, what kind of laws of motion does the body follow once it leaves the ice? The answer to this question was revealed by Galileo in the 17th century. He found that all projectiles will follow a beautiful parabolic trajectory. This ancient law is reflected in every figure skating jump. From the moment the skater pushes off the ice, their trajectory is already dominated by gravity. No matter how you wave your arms or pull your legs together in the air, you cannot significantly change the established parabolic trajectory of your center of mass, though you can still control your posture and rotation. That's why coaches are so demanding about takeoffs. That decisive moment is directly related to the precious time in the air, determining whether the skater can complete the planned 3 or 4 revolutions. When the parabolic trajectory in the air comes to an end, it appears the skater will only glide smoothly on the ice. The TV slow motion often makes this moment seem as gentle as a feather landing. In fact, according to kinematic measurements, at the landing moment of a difficult jump in figure skating, the skater's ankles and knees can experience forces 5 to 8 times their body weight. If they landed directly on a hard floor, the joints and bones could not bear it. The body must divide this energy into several parts and slowly absorb it. At the moment of first contact with the ice, the tiny contact point between the blade and the ice creates huge pressure, temporarily softening the ice. Then the skate slides forward in the direction of motion, and the contact area gradually spreads out into a line. The friction and squeezing between the skate and the ice dissipate the impact energy little by little, instead of it all hitting the knee in the same millisecond. So when landing, skaters bend their knees, and their bodies compress like a spring. This lets their muscles and joints cooperate with the skates to break the impact into a long and soft landing. This raises a deeper question. Why is ice so forgiving? This question drew the attention of 19th century physicists. A group of scientists became interested in the true nature of ice, and 19th century scientists demonstrated this with an experiment that was often replicated later. They took a large piece of ice, put a thin metal wire over the middle of the ice and hung weights on both ends. After a period of time, the metal wire slowly cut into the ice and finally passed completely through the ice. But when they picked up the ice, they found that the ice cube was not cut in half, but was reconnected into a whole piece, as if the cut had been sewn together. Scientists realized from this that ice is not a completely hard brick, but a substance that can be softened locally and then returned to a solid state. Later, people called this phenomenon, where ice melts and then refreezes once the pressure is released, regelation. If you look back at the blade marks on the ice rink, you will understand that the groove pressed by the ice skate is only written on the ice for a short time, and then it will slowly close and heal in the cold. In the mid-19th century, the Thompson brothers went further. They found that the higher the pressure, the lower the melting point of ice. Let's go back to the ice rink. You will notice that the ice skates are very thin. A skater's weight is concentrated on a narrow metal blade. This blade leaves not a permanent mark on the ice, but a temporary track that can be slightly rearranged and slightly softened. When the skaters skate away, these slightly squeezed and loose ice molecules slowly return to a more stable position. The indentations become shallower, and the surface becomes solid again. When the ice resurfacer comes up to scrape the lifted ice chips and polish the surface again, the ice that was just carved with gullies quickly becomes like a blank page in a new book, waiting for the next skater to write new arcs on it. From Galileo's parabolic motion, to the discovery of the wonders of ice, to the pressure melting principle revealed by the Thompson brothers, and finally the partial healing of the ice surface. All these together constitute the invisible wings that allow skaters to fly. On the ice rink, we jump, we spin, we fall. The blade leaves a thin trace on the ice, but soon it is smoothed over by the cold air, as if it never existed. Life is no different. The choices we make, the risks we take, the people we love, and the detours we face may not leave visible traces forever. They just leave a mark on the ice of time and are then quietly erased. This is a physical law that no one can resist. But when you step on the ice rink again, knowing that these traces will eventually disappear, would you still choose to jump?